All right, welcome back. We are now in Module 6, and in Module 6 we're going to learn about continuous probability distributions. And this includes the uniform, the normal, and the exponential probability distributions. In this video we're going to go through this slide. You can pause the video and take a look at it. We're going to go through this slide. You can pause the video and take a look at it. You can go through this slide, pause the video, take a look at it. And we're going to go through this slide, pause the video if you want, take a look at it. And continuous differs from discrete in the sense that discrete are whole numbers. Like when you're measuring the number of customers coming into your store, you're going to measure whole numbers. And I got to look up what is a whole number. Please tell me what is a whole number. Let's go here and we'll create a new chat here because this was for Module 5. So we'll do here and we'll say, please tell me what is a whole number. I think whole number, it's just got to be whole. It's like 1, 2, 3, 4, 5. So a whole number is any number that is non-negative and does not have a fractional or decimal part. In other words, it's a number that belongs to the set of numbers 0, 1, 2, 3, 4, 5, so on and so forth. So that's exactly what I was looking for. And I'm going to rename this chat here. So right click it. And I'm going to call it stats mod 6. So that will also be available. All these chats, I'll put them into our resources for our course on Canvas. So we're talking about continuous probability distributions. And that's different than discrete probability distributions. So in the previous module, we were looking at discrete probability distributions, bivariate probability distribution, binomial, hypogeometric, Poisson, and that kind of stuff. So that was discrete, but now we're looking at continuous. And when we looked at discrete, let me see if I could find an example. Hold on. All right, here's an example. So when we looked at discrete, it's like number of cars sold during the day. Like our variable could randomly be any of these. And when we have one of these variables, this is the probability of that event occurring that day. And so we could have 0, 1, 2, 3, 4, 5 cars. And this is what the discrete probability distribution would look like if we graphed it out, which is graphed out here. And this is probability over here. And you can see that it's discrete, right? It's like you don't have fractions. But when we compare that to continuous, you have a whole bunch of, an infinite number of possible values between 0 and 1, right? It's continuous. And so you get something that is a curve like this with the normal distribution, or with the uniform distribution, you get like a box, right? Where your value could be any fraction. Like if this was, like the example in the textbook is how long is the flight time between Chicago and New York or something like that. And this would be like 120 minutes to 140 minutes. And it could be any value between 120 and 140. Like let's say in the entire sort of, and I'm just trying to think of the phrase, hold on one second because it's a little bit later, wait one moment. All right, there's the phrase. I wanted to bring this up for you to look at. So in the entire sample space of all of the possible values that have ever been recorded and all the possible values that could exist, flight times have only been between 120 and 140 minutes in that example in the textbook. And so, you could say, what is the probability that it's going to be between 115 and 120 minutes or whatever? But that is like, it's continuous. It could be, it doesn't have to be 120 or 121. It could be 120 minutes and 43 seconds and fractions of a second. So it's continuous distribution. And here we have another distribution, exponential. And so we'll learn about these different probability distributions. And to begin learning about them, I'm going to download this slide as, I don't know, PNG. I'm going to go to ChatGPT and say, can you, and maybe I'll change my, can you please explain the information on the attached slide image. And then I will go get that slide and upload it from my computer. I'm going to upload it. And so here is chapter 6 right there. That's the slide. And I could go clean up some of that stuff while this runs. I'm going to pause this while that generates. All right, that should be done generating. And oh, the request chimed out. I'm going to regenerate. I'm going to pause this again. Hold on. All right, so here we are. The slide presents 3 types of continuous probability distributions. These distributions represent situations where the possible outcomes are continuous values, i.e. they can take on any value within a range rather than distinct values. And again, this is a distribution of the probability of, finding some amount in a certain range, right? So, the distributions represent situations where the possible outcomes are continuous values. They can take any value within a range rather than distinct values. A uniform probability distribution, in the top right, the graph of the uniform probability distribution is shown as flat rectangular shape. This distribution represents outcomes, so here's that flat rectangular shape. This distribution represents outcomes that are equally likely over a certain range. Every value within this range has the same probability. Example, you randomly select a number between 0 and 1. All numbers in that interval have a chance, an equal chance of being selected, right? So 0.72, right? So, all numbers have an equal chance of being selected between 0 and 1. Normal probability distribution, that's this one here, normal. And that one there is the bottom left image shows normal distribution, often represented by a bell-shaped curve. This distribution is symmetric with the majority of values clustered around the mean. So the mean would be right here in the middle. The mean, the median, and the mode would all be right there in the middle. And you have symmetry on the left and right side. This distribution is symmetric with the majority of values clustered around the mean. The probabilities taper off as values move further from the mean. Example, the heights of people in a large population typically follow a normal distribution, where most people are of average height and fewer people are very tall or very short. And remember, what this stuff is all about is calculating probability, right? So what, we could say people from here, well, I'm just moving that slide. We could say, we could say people from here to here, what percentage of them, what's the probability if we, were to look at the population that this percent of the population would be in this range from here to here, plus or minus 1 standard deviation, or plus or minus 2 standard deviations from the mean, right? We could start to figure out the probability of certain heights occurring if we were to select somebody from the population. Exponential probability distribution, the bottom right displays exponential distribution, characterized by rapidly declining curve. This is the exponential. This distribution is commonly used to model the time between events in a Poisson process. So Poisson is, again, like the time between phone calls at a call center would be measured by an exponential probability distribution. So the time between phone calls, as we increase the time, right, between phone calls, x, the probability that we're going to have 10 minutes between a phone call is much lower than the probability that we're going to have 10 seconds between a phone call. And so that's the exponential distribution. So an example, the distribution is commonly used to model, we just saw that. The time you have to wait before the next bus arrives can often follow an exponential distribution. So, it's a low probability that you're going to wait 29 minutes and 48 seconds. That's only if you just missed the bus, if it comes every 30 minutes. And there's a higher probability that you'll wait less time. So those are 3 examples. Let's look at the next slide. So the next slide, continuous probability distributions. A continuous random variable can assume any value in an interval on the real line or in a collection of intervals. So this is just describing what continuous is. And on a linear interval, or which is a line, or a collection of intervals, the value could be anywhere between 1 and 2. Like if that was our line, it could be 1.74. It's continuous. It is not possible to talk about the probability of the random variable assuming a particular value. This is like, for me, I don't totally buy this. Like, I'm skeptical of this because, like, why is it not possible? But they say, the probability that you land on some really small, fraction of a fraction of a fraction, that's part of maybe their thinking, that they say you can't talk about the probability of the random variable assuming a particular value. So I don't know about that, right? I'm still, the verdict for me is out on that, and I'll say a little bit more about that in a second. But when you do talk about continuous probability distributions in statistics, we talk about the probability of the random variable assuming a value within a given interval. So if this was flight times right here, right, and it's 120 to 140, we might say, what's the probability that we're going to get in there from 125 to 135? And we can look at that probability. Or we could say, what's the probability that, if we choose somebody, their height is going to be between here and here. Or what percentage of the population is this tall or less? Or what percentage of the population is this tall and more, right? And so we look at those probabilities over a range when dealing with continuous probability distribution. So you don't really think about it in terms of it being a single value with continuous probability distributions, but what's the probability of a value being found over a range or a certain range occurring, right? So that's the probability. So here's an example of that, like, what's the probability from here to here, or the probability of, the values being from here to here, or the probability of the values being from there to there. The probability of a random variable assuming a value within some given interval is defined to be the area under the graph of the probability density function. So these are called probability density functions. This is another example in my book of statistics having an inferiority complex and making things overly complicated, but also every domain has its own terminology. And so they call this probability density function. These are probability density functions. So what's the probability of a random variable assuming a value within some given interval? So what's the probability that someone's height is between here and here? And we could, between this height and that height, we could find that out if this was the, normal probability distribution of heights. We could figure that out, and we're going to see how to do that, because it's about probabilities. What's the probability of that occurring? And so the last thing here is that the area under the graph, right, of fx and probability are identical. So this area under here and probability are identical. And so you could also say that we could just calculate the area, and then that gives us the probability. So we could say, this is, what is it, width times height. We could say the width times the height will give us this probability here. So that's just an interesting little anecdote that's included in the book and also here in the presentation. This is valid for all continuous random variables. And the probability that x takes on a value between some lower x and some higher x can be found by computing the area under the graph from the interval x1 to x2. So calculate the area here, and the probability that the value could be between this point and that point. It's pretty straight. It's pretty clear from the drawings that that's the case, but they're just making it extra clear by pointing it out here. And that's leads to this saying area is a measure of probability, right? So this area is a measure of probability. Again, overcomplicating things, if you ask me. So that's an introduction to continuous probability distributions and the three type we're going to look at: uniform, normal, and exponential. Quite frankly, I don't know if there's more because I'm just new to teaching statistics. This is my second semester. Took it, of course, in grad school and as an undergrad, but here we go. Learning it and studying up. So I'm learning with you, right beside you. And so here is what we're going to see in the next video. We're going to take a deeper dive into uniform probability distribution. See you in the next video.